The plate heat exchanger model HE200 has been designed to allow students to get familiarized with the operating of plate heat exchanger and to collect the necessary experimental data for the calculation of the heat losses, heat transfer coefficient, log mean temperature difference, etc. Students will also be able to study the effects of flow rate on the heat transfer rate. Later, students may apply this knowledge to complex industrial plate heat exchanger. The HE200 comes with alpha Laval plate heat exchanger and two stainless steel sump tanks for the hot and cold water supplies. The hot tank is fitted with 34.5 kW tubular immersion heater that are protected against possible overheating. Each tank is equipped by a centrifugal pump capable of delivering 20 liters per minute of water. The pumps are protected from dry run by an electronic lever switch installed inside in each of the sump tanks. A low level in the cold water tank will automatically cut the electrical supply to the pump, and a low level in the hot water tank will electrically cut the supply to the heater and to the pump.
Hi guys, okay, so firstly, we need to turn on the main switch. And then, we turn on the heater and the pump 1 and the pump 2. So, this thing, the FT1 is for the flow rate for hot water. FT2 is flow rate for cold water. And this indicator is for the temperature. This is the inlet for hot water. T2 is outlet for hot water. And for cold current, T3 is the inlet. And for cold current also, the T4 is the outlet. For counter current, it is the opposite for T3 and T4, which is for counter current. T3 is the outlet and the T4 is the inlet. So for the temperature, you can also read it from the gauge. It is located over here. So be careful to not touch the hot surface. Okay. Then you can also read the temperature from the visualized reader here. You can see this is the temperature, 70. So to increase the temperature to our targeted temperature, we must press this button. So in this case, we'll be changing from 50 to 55. So first we press this button, and then we change it, we increase it to 55. Okay, so that's all.
Okay, so for the general procedure, we will have some equipment that we have to take note. So the first one, this is the valve. So we close and open the valve according to the flow that we want to create. Either it's counter flow or it's cold current flow. Okay, next one, this is the rotameter. So the rotameter is at both hot tank and the cold tank. So the rotameter, the function is to take note about the volumetric flow rate of the flow. Then we have here also, this is the turbine flow meter for both the hot and the cold tank. The turbine flow meter is also to measure the amount of flow rate inside the pipe. Okay, so this is the cold water tank. There are two tanks, the cold water tank and also the hot water tank over there. So below the tank there is a drain and also a pump. So this is the pump to increase the pressure so that the water will flow into the pipe. So there's two pumps, one for each water tank.
So this pipe show for the counter current system. So we're gonna switch to cold current system. We're gonna close H10 and H9. And we're gonna open H11 and H8. So this show for the cold current system. So To reach the targeted flow rate, we must adjust the valve. And our eyes must perpendicular.
Alright, so if you want to know if the valve is closed or open, for this valve you can see that if you rotate it clockwise, it will be closed. If you rotate it anti-clockwise, it will be open. But for this valve, you can see if it is in line with the pipe, then it is open, but if it is perpendicular with the pipe, then it is closed. So next is about the plan. So if you are unsure where to find the valve and all the equipment, you can refer this plan to find the correct valve that you can set. So for the two experiments, which is co-current and counter current, you can refer like manual page 131 to make sure that you properly close and open the valve according to the experiment.
After the experiment is done, you have to switch off the heater, pump 2, pump 1, and the main switch. And don't forget to close all the valves.
So, for the result and discussion part, we will discuss first for the variation of flow rate in the hot water. So, the first graph will show the overall heat loss, Q loss versus mass flow rate of hot water. From this graph, it shows that the heat loss for cold current increases, while for the counter current it decreases from the first mass flow rate to the second mass flow rate. Then it remains increased for the next 3 mass flow rate. Heat loss has been calculated according to the formula Q equals to mCp delta T. Next, the next graph shows the mean thermal efficiency and the mass flow rate of hot water. From the graph, it shows that the value of the mean thermal efficiency for the counter current is higher than the cold current. For the cold current, the values of the mean thermal efficiency is consistent from the first mass flow rate to the last mass flow rate. This is because the cold current flows create a more constant wall temperature than the counter current.
For the result of variation for mass flow rate of cold water shows the relationship between overall heat loss and mass flow rate of cold water. In this result, counter current has higher values than cold current. Both flows increase due to the mass flow rate. For cold current, it decreases from the fourth mass flow rate to the last mass flow rate. Based on the graph of mean thermal efficiency against mass flow rate of cold water that we've plotted, the mean thermal efficiency of counter current is higher than the mean thermal efficiency of cold current. The plotted line for cold current flow is consistent for each reading because cold current flow constructs a higher constant wall temperature than counter current flow.
Okay, so next for the variation in temperature. The graph shows that the overall heat loss against temperature of hot water. This figure shows both graphs for cold current and counter current are not consistent. The graph shows as the overall heat loss increases when the temperature of hot water also increases. The graph of overall heat loss of the counter current flow is higher than the cold current flow. This overall heat loss can be calculated using the formula Q equals to mCp delta A. So lastly, the last graph shows the mean thermal efficiency against the temperature of hot water. The graph shows the plot line of the mean thermal efficiency for counter current is higher than the cold current. The thermal efficiency of hot water and the thermal efficiency of cold water are determined first, and then the mean of thermal efficiency is calculated.
The objective of the experiment is to observe the efficiency of a heat exchanger according to two flow arrangements which are counter current and co-current through heat transfer efficiency and thermal efficiency. Each flow is then divided with 3 different manipulated variables which are hot water flow rate, cold water flow rate and hot water temperature. It can be concluded that countercurrent flow is better than co-current flow for a heat exchanger, mostly because of a more even distribution of heat across the heat exchanger throughout the whole process due to consistency of temperature difference, which allow the maximum efficiency.
Okay,
That's all from us. Thank you.